Welcome back to the review lectures for energy balances. We have looked at all the fundamentals associated with energy balances, and in the last lecture we actually performed a multi-unit process where energy balances were performed for a phase change operation. Today we will start performing another energy balance calculation. Here we will actually be looking at a process where there is a reaction. So, we will be looking to perform a simple energy balance calculation for a system with a reaction. However, we will also see how it would be applicable for a closed system, and we will look at different aspects associated with energy balances for a reactive process while we solve this example problem. So, here is the problem. The thermal decomposition of dimethyl ether, which is shown here, is dimethyl ether forms methane, hydrogen and carbon monoxide, is to be carried out in an isothermal 2-liter laboratory reactor at 600 degrees Celsius. The reactor is charged with pure dimethyl ether at a pressure of 350 torr. After about 2 hours, the reactor pressure is 910 torrs. Has the reaction proceeded to completion at the end of the 2-hour period? If not, what percentage of the dimethyl ether has actually decomposed? Taking elemental species at 25 degrees Celsius as the reference state, prepare and fill an inlet and outlet enthalpy table. Use the following data for dimethyl ether. Heat of formation for dimethyl ether is minus 180.16 kilojoules per mole. Cp for dimethyl ether is, in terms of kilojoules per mole Kelvin, is given as 26.86 plus 0.1659 T minus 4.179 times 10 power minus 5 T squared, and temperature here is in Kelvin. So, this is to be taken carefully. So, if you have the T value, the temperature value in Kelvin, you should appropriately use the right units for the Cp value. Using the value calculated in part B, you are asked to calculate delta HR cap at 600 degrees Celsius and delta UR cap for dimethyl ether decomposition reaction. You are also asked to calculate the standard heat of reaction for dimethyl ether reaction, and you are asked to calculate how different this value is from the heat of reaction at 600 degrees Celsius that was calculated in the previous part. How much heat was transferred to or from the reactor during the 2-hour period. So, now let us look at this problem. So, here in this problem we actually have been given the initial and final pressure conditions for a closed system, and we have been asked to calculate what would be the conversion in this process. So, how would we do that? So, assuming ideal gas behavior, we will be able to calculate the number of moles which is present initially and finally, and from that we should be able to arrive at what would be the conversion which we are looking at. Let us try and do that. Assuming ideal gas behavior, we have PV equals nRT as the ideal gas law. So, pressure has been given as the initial condition as 350 torr. So, this can be converted to SI units, which is Pascal, and you would get 46,662.829 Pascals. So, 1 torr is equal to 133.3 Pascals. So, using that roughly you will be able to get this value, and V, which is volume, is 2 liters, which can then be written as 2 times 10 power minus 3 meter cube. So, I am converting everything to SI units so that it will be easy to use the R value directly. R is 8.314 joules per mole Kelvin, and you have temperature T, which is 600 degrees Celsius, and in SI units it would be 873 Kelvin. So, you can substitute these values to the equation ideal gas law, and you will have N equals PV by RT, which is equal to 46,662.829 times 2 times 10 power minus 3 divided by 8.314 times 873, and you would end up with a value for N as 0.01286 moles. So, that is the initial number of moles in the system. So, the final condition has been given as, so this the values we have done is for initial condition. So, for final condition we know that the pressure is 910 torr. So, if we were to assume that x moles of dimethyl ether which was initially given is consumed. So, we have 0.01286 moles of dimethyl ether initially. If we assume x moles of that actually was consumed, the final state would actually contain 0.01286 minus x moles of dimethyl ether, right. So, this would be the number of moles of dimethyl ether. Looking at the stoichiometry, we know that for every mole of dimethyl ether consumed, we would have 1 mole of methane, hydrogen and carbon monoxide produced. So, if x moles of dimethyl ether is consumed, you will have x moles of methane, x moles of carbon monoxide and x moles of hydrogen present in the system after the reaction is completed. So, this would mean that the final number of moles, would actually be equal to 0.01286 minus x plus x plus x plus x, which is equal to 0.01286 plus 2x number of moles. So, this would be the number of moles in the final condition. So, now we need to calculate what x is for us to know what would be the conversion in this process. Using the ideal gas law, we would actually be able to identify the final number of moles, and from there we can actually calculate what x is, so that we can get the conversion for this process. So, what we would have is P final V equals N final RT. So, here volume is constant because it is a constant volume vessel of 2 liter volume, and temperature is also a constant because we have been told that it is an isothermal process. So, we can calculate NF from here, and we know the final pressure is P final is 910 torr. So, we can convert this to pascals, and from there we will be able to calculate the final number of moles, which would be N final would be equal to 0.03343 moles. So, from here we can calculate x. We know that N final was equal to 0.01286 plus 2x based on stoichiometry. This is equal to 0.03343. So, x would be equal to 0.010288 moles. So, this x is the number of moles of dimethyl ether which has actually been consumed. So, conversion of dimethyl ether would be equal to 0.010288 divided by 0.01286, which is the number of moles of dimethyl ether consumed divided by the number of moles of dimethyl ether fed times 100, which would be equal to 80%. So, 80% of dimethyl ether which is fed is actually consumed in this process, which means the reaction is actually not going to completion, only 80% of the reactant is getting converted. In the second part of the problem, we have been asked to build the enthalpy table by assuming elements at 25 degrees Celsius and 1 atmosphere as the reference state. So, let us try to do that. So, this would be the heat of formation technique for calculating energy balances if we were to perform that. So, here we are only asked to build the table and complete the table. So, let us do that. So, the reference state would be carbon solid, hydrogen gas and oxygen gas all at 25 degrees Celsius and 1 atmosphere. So, this is the reference state. So, assuming ideal gas behavior, we will not have to worry about change in pressure. So, we will only use the temperature effect on enthalpies. So, the substances which we have are dimethyl ether, so CH3 twice O, then you have methane and hydrogen and carbon monoxide, which are all present in the system. So, N initial and you have H cap initial, N final and H cap final. So, we need to build this table and complete this table. So, far as the number of moles of dimethyl ether fed, you have it as 0.01286, number of moles of dimethyl ether which is remaining would be 0.2 times 0.01286. So, based on stoichiometry, the number of moles of methane fed would be equal to the number of moles of dimethyl ether consumed, which would be 0.8 times 0.01286, and this would also be the same would be the values for hydrogen and carbon monoxide as well. So, it will be 0.8 times 0.01286, 0.8 times 0.01286. So, you do not have any methane, hydrogen or carbon monoxide in the initial condition. In the final so in the initial and final condition, we now need to identify which enthalpies will go to 0 and which enthalpies have to be accounted for. So, let us say we have to identify H1 cap for dimethyl ether. So, dimethyl ether initial condition is at a temperature of 600 degrees Celsius, and you are going to have the reference states as carbon, hydrogen and oxygen and 25 degrees Celsius on 1 atmosphere. So, there is definitely a change in enthalpy here. So, what about the dimethyl ether enthalpy for the final condition? So, here the pressure is different, however, the temperature is still the same because it is an isothermal process, which means the enthalpy would still be the same because we are going to ignore the effect of pressure for an ideal gas, and as we are assuming ideal gas, we will ignore the effect on pressure. So, you will be left with the same value of enthalpy for dimethyl ether for the initial and final condition. We need to calculate the enthalpies for methane, hydrogen and oxygen for the final conditions as well. Now, let us go ahead and calculate these values H1 cap, H2 cap, H3 cap and H4 cap. So, what is H1 cap? So, H1 cap is nothing but the process where you first have the reference state, which is carbon solid, hydrogen gas and oxygen gas at 25 degrees Celsius and 1 atmosphere, forming dimethyl ether at 600 degrees Celsius, which is the initial condition. And let us look at this. So, you have to consider this as a single step process. So, which means we have to build a hypothetical path to identify the change in enthalpy, because you have formation happening and we need to identify change in temperature as well. So, this can be broken down into 2 steps. The first step would be the formation of dimethyl ether. So, CH3 twice O at 25 degrees Celsius, and from here it can be heated to 600 degrees Celsius. The first step is the formation reaction and the second step is the change in temperature. So, this means H1 cap would be equal to the standard heat of formation for dimethyl ether plus integral 298 to 873 Cp of dimethyl ether dt. So, I am using 298 and 873 because the Cp value which has been given to us in the problem was had stated that the temperature used in the Cp value is in Kelvin. So, I am using the temperature value in Kelvin. So, if we were to substitute the values for heat of formation and the Cp values, we would actually get minus 180.16 plus 62.4, giving H1 cap as minus 118 kilojoules per mole. So, this is H1 cap. Now, let us look at H2 cap. So, H2 cap is basically again a similar thing where you have the first step, which is the heat of formation, the formation of methane from carbon dioxide, from carbon and hydrogen gases, carbon solid and hydrogen gas. So, now you have heat of formation, standard heat of formation as the first step. So, heat of formation of methane plus integral Cp of methane dt, and the temperature again would increase from 298 Kelvin to 873 Kelvin. So, using the Cp value for methane from the tables and the heat of formation for methane, we can actually calculate this as minus 74.85 plus 29.46, giving a value of minus 45.39 kilojoules per mole. So, H3 cap can actually be obtained directly from the tables which are available for combustion gases. So, you have hydrogen gas which is which is present in the final condition at 600 degrees Celsius. So, taking that from the reference state, you can actually calculate this and this value would be 16.81 kilojoules per mole. And H4 cap, here again you have carbon monoxide formation and then heating of carbon monoxide. So, the first step would be the heat of formation of carbon monoxide, and in the second step we do not have to look up, we do not have to do integral CPdT, we would be able to get the enthalpy value for carbon monoxide with reference to 25 degrees Celsius from the combustion gases table. So, you have H cap CO at 600 degrees Celsius, and this would be equal to minus 110.52 plus 17.57 giving minus 92.95 kilojoules per mole. So, now we have all the enthalpies and we can fill the enthalpy table. Substituting the values we obtained into the enthalpy table, we would have dimethyl ether, methane, hydrogen and carbon monoxide. We will have to fill in N initial, H cap initial, N final and H cap final, and from here we would have 0.01286 and zeros here with 0.002572, 0.010288, 0.010288, 0.010288. So, enthalpy would be minus 118, minus 118, minus 45.39, 16.81, minus 92.95, and with this the enthalpy table is complete. So, for the third part of the problem, we have been asked to calculate the heat of reaction at 600 degrees Celsius using this table. So, how would we do that? So, we can actually calculate delta H from this, and if we have the extent of reaction, we have always been using extent of reaction times heat of reaction as the change in enthalpy for the process, whereas now we will do the other way, we will actually calculate heat of reaction from that equation. So, we will calculate delta H from here. So, delta H will actually be from this table, you can actually calculate the enthalpy of the final condition minus the enthalpy of the initial condition. The final condition enthalpy is minus 1.5538 and enthalpy of the initial condition would be minus 1.51748. So, giving you a delta H of minus 0.03632 kilojoules. And we need to now have the extent of reaction if you want to calculate the heat of reaction, because delta H is also equal to xi delta HR at 600 degrees Celsius. So, now we need to know the value for xi, which is the extent of reaction. We can calculate the extent of reaction xi as follows. Using methane final and initial amounts, we would actually have 0.010288, which is the final, minus initial would be 0 divided by the stoichiometric coefficient of methane, which would be 1, giving you the extent of reaction as 0.010288 moles. So, from here we can calculate delta HR cap at 600 degrees Celsius as minus 03632, which is the delta H we calculated, divided by 0.010288, giving a value for delta HR cap at 600 degrees Celsius as minus 3.53 kilojoules per mole. So, we have also been asked to calculate delta UR cap at 600 degrees Celsius, and this would be equal to delta HR cap at 600 degrees Celsius minus RT times the summation of gaseous products stoichiometric coefficient minus the summation of the gaseous reactants stoichiometric coefficients. So, this would mean minus 3.53 kilojoules per mole minus 8.314, which is the value for R, times 10 power minus 3, because everything is in kilojoules, I am converting it into appropriate units, and you would want to multiply it with the temperature, which is 873 Kelvin, times the gaseous products are actually 3 moles. So, 1 plus 1 plus 1 minus 1 which is the reactant. So, this would give delta U r cap at 600 degrees Celsius as minus 18 kilojoules per mole. So, you have calculated delta H r cap and delta U r cap for 600 degree Celsius condition. So, the next step is to identify the standard heat of reaction. So, how would we find the standard heat of reaction? So, that we can actually get using the heats of formation for the compounds and compounds which are present in the reaction. So, using the heat of formation, you would have the standard heat of reaction would be equal to sigma of products where stoichiometric coefficient times standard heat of formation for a compound minus sigma of reactants stoichiometric coefficient times the standard heat of formation. So, you can get the values for the standard heat of formation from the tables, and using the values from the tables and whatever data has been given, this value can be calculated as delta H r cap standard would be equal to minus 5.21 kilojoules per mole. So, as you can see, it is significantly different from the heat of reaction at 600 degrees Celsius. At 600 degrees Celsius, the heat of reaction was minus 3.453 kilojoules per mole, whereas here it is minus 5.21 kilojoules per mole, almost a difference of 50% compared to the 600 degrees Celsius. So, now the last part is to calculate the amount of heat that needs to be transferred to the reactor for the process to actually happen. So, this is a closed system. So, we would actually have to calculate only the, so here the only effect is the heat of reaction, and we are, because it is isothermal, there is no effect on temperature. So, you will be able to use the internal energy of the reaction directly. So, the equation actually is Q minus W equals delta U plus delta Ek plus delta Ep, as usual Ek, Ep and W go to 0, and you are left with only delta U, and delta U would here would actually only be xi times delta U r at 600 degrees Celsius. You have the heat of reaction, the internal energy of reaction at 600 degrees Celsius, which can be directly used. So, doing that you would get Q equals minus 0.185 kilojoules. So, with this we have solved this problem, and we are at the end of how to perform energy balances for a closed system, and we have also looked at how simple pressure data could be converted to moles and so on, and to calculate conversion and so on. So, we actually we have completed this problem, and in the next lecture we will look at one more which looks more like a case study, which tries to apply all the concepts we have learned from the material balances and energy balances, and that will give us an overall review of all the fundamentals that we have learned. Until then, thank you.